Hello everyone, my name is Ashwin Devanayagam and my teammates are Parivel N and Varunesh S. Our project for our final year is AI agents for drug repurposing. This project was done under the guidance of Dr. Revati ma'am. So first of all, let's talk about what drug repurposing means. Drug repurposing is the process of identifying new therapeutic applications for existing drugs. Since these drugs may already have known safety profiles, manufacturing processes, and pharmacological information, repurposing can reduce the time, cost, and risk involved in developing treatments. Our project uses multiple specialized AI agents to evaluate drug repurposing candidates using evidence from different biomedical domains. Why we have the traditional drug repurposing and its limitations. So why drug repurposing involves manually reviewing traditional drug repurposing involves manually reviewing scientific publications, conducting laboratory screening, studying biological mechanisms, and examining clinical observations. Although this approach has produced successful treatments, it is time consuming and requires significant expertise and resources. Relevant evidence is actually distributed across research papers, clinical trial databases, safety reports, biological databases, regulatory records, and patent sources. The available evidence may also be contradictory. A drug may have a promising biological mechanism, but limited clinical evidence or significant safety concerns. General purpose AI models can summarize information quickly, but they may produce unsupported claims. Therefore, researchers require an evidence which is grounded and explainable and is an explainable system. Our proposed solution is a multi-agent biomedical reasoning framework. Instead of asking one AI model to provide a direct recommendation, the system divides the analysis among specialized agents. The framework actually combines biomedical entity normalization, multi-source evidence collection, semantic vector retrieval, retrieval augmented generation, specialized AI agents, contradiction detection, validation, governance-based scoring. The system acts as a research support tool. Its recommendations are intended to prioritize candidates for further investigation and not replace biomedical experts or clinical trials. So first, so let's start with how this project works. So first, it is input and evidence collection. The process begins when a researcher enters a drug disease pair through the React-based web interface. So, for example, let's say the drug interface is paracetamol and diabetes. So first, that drug that input is actually sent is actually sorry, the fast API backend first performs entity normalization. The drug names are normalized using RxNorm, while disease names are normalized using mesh terminology. The data pipeline then collects information from multiple sources. PubMed for scientific retrieval, clinicaltrials.gov for clinical studies, OpenFDA for safety events and drug labels, UniProt for biological targets and mechanisms, patent sources for intellectual property evidence. This evidence is organized into literature, clinical, safety, mechanistic, market, and patent domains. Next, the collected documents are divided into smaller overlapping text chunks. Each chunk is converted into a 384 dimensional embedding using the all-mini-LM L6V2 sentence transformer model. The retrieved evidence is passed to the language model through retrieval augmented generation. So before that, those embeddings are stored into Quadrant, which is a vector database. Quadrant allows the system to retrieve the evidence based on semantic meaning rather than using the exact keywords. The model is then instructed to analyze only the retrieved evidence and return a structured result containing support, confidence, contradiction status, and a short summary. This reduces the unsupported outputs and improves explainability. So after that, we have the framework actually defines 6 specialized agents. The safety agent, which analyzes the adverse events and acts as the first safety gate. The literature agent evaluates research publications. The mechanistic agent examines biological pathways and the drug's mechanism of action. The clinical agent evaluates clinical trial evidence. The market agent examines indications, availability, and regulatory information. Patent agent evaluates intellectual property constraints. These agents are coordinated using Landgraph. The safety agent executes first. If safety is cleared, the literature and mechanistic agents execute concurrently. Then the clinical, market, and patent agents execute concurrently. If an agent returns invalid or low confidence output, it reformulates the query and performs a second attempt. Now we go to the contradiction detection and validation. After the agent's execution, the system compares the results from different domains. If two confident agents disagree, the contradiction detector creates a contradiction flag. For example, literature evidence may support a candidate while clinical evidence does not. The system records this disagreement instead of incorrectly presenting a consensus. The validation layer then checks whether enough usable evidence exists. The current implementation requires at least two valid non-safety agent outputs and a minimum average confidence of 0.20. If evidence is insufficient or critical contradictions exist, the candidate is rejected due to insufficient evidence. Now, the governance decision engine. After validation, the governance engine calculates the final score. Uh, each domain receives a different weight. Safety has 30% of weightage, literature has 25% weightage, clinical has 20% weightage, mechanistic has 10% weightage, market has 10% weightage, and patent has 5% weightage. The contradiction reduce the score. Actually, these weightages have been assigned through the basis of papers, and in those papers, of research papers actually, in those research papers, we have found out that during the process of drug repurposing, this is how the weightage for each domain is assigned during the research process. So back to where we were talking about, contradictions reduce the score while agreement between at least three confident agents provides a small boost. A strong safety signal forces the final score to 0. The final recommendation is classified as approved when the score is at least 0.5055, conditional when the score is between 0.30 and 0.55, rejected when the score is below 0.30 and the safety fails or the validation fails. Again, this is how traditional drug repurposing works. We have applied that same framework in our project. An approved result means recommended for further research. Most importantly, it does not, and I mean it does not mean that the drug is medically or legally approved for proposed disease. Now let me just talk about the tech stack that we've been using. The tech stack that we for front end has been developed using React and Vite, while the back end uses FastAPI. Quadrant provides semantic vector retrieval, LangGraph coordinates the agents, and Ollama runs the language model locally. MongoDB can store previous analysis sessions and audit logs. The repository also supports generating PDF research, reports containing agent findings, governance scores, contradictions, and recommendations. Compared with the traditional drug repurposing, our solution automatically examines multiple evidence domains, identifies contradictions, prioritizes safety, and explains how the final recommendation has been produced. It helps reduce the effort required for preliminary evidence review while keeping researchers involved in the final decision. Now, since I've explained what the project does, let us now go for a demo. My apologies for that. Now, since I have explained the entire project in theory, let us now look at a practical application of how the project works. So here, as we can see, the drug disease pair that we have given is paracetamol and the disease is diabetes. So the hypothesis, the governance that we have been given is approved with a confidence score of 72.6%. It is actually a good score. Why we have been given this is because the mechanism modeling suggests that the drug induces a conformational change in the primary protein structure of the disease, which effectively blocks the pathological signaling cascade while maintaining bioavailability at the target site. Now this is the outputs given by different agents. As you can see, there's only a problem. We only have a problem with the patent agent. So this is our final year project. Thank you very much for watching.